Hi everybody. In today's lesson, we are going to talk about measurement and systems of measurement in physics. So the first thing to talk about is that if we want to be able to communicate measurements to other people, then we have to have some sort of standard by which we measure things. So standardized systems are going to be agreed upon by some authority, a governmental body, something like that. So the one that we use in physics is called the SI system, and it stands for Système International. So this was first set up in France, but it was agreed by many different countries to be used for scientific purposes, and that was back in 1960. And that's going to be the main system that we use in our course. All right, we don't have a textbook per se, but this is the system of measurement that we're going to use. And the SI system is essentially the metric system, so we're going to use that. The major advantage to using the metric system is that we have prefixes that correspond to powers of 10, meaning every single unit that we use in the metric system is a power of 10 change to convert, for example, from centimeters to meters, all right, from grams to kilograms, things like that. So we don't have to worry about remembering things like, oh, there's how many feet in a mile again, or, things like that. Everything is based on powers of 10. So it's 10, 100, 1,000, 1/10, 100th, 1,000th, etc. Each prefix has its own name and its own abbreviation. Okay, so if we look down here on the right, you can see there are tons of different powers of 10 and the prefixes that go with those, and then the abbreviation for each one. All right, I don't expect you to know all of these. If you were given a chart, then you could take a look. However, there are a couple that I do want you to memorize. So the three that you're going to see the most in this course and that you're going to use the most in this course are going to be milli, which is 10 to the negative third. That's 1,000th. Or centi, which is 10 to the negative second. That would be 100th. Think cents versus dollars. All right, or kilo. All right, which is 10 to the third. That would be 1,000 times whatever you have. So kilo is easy to remember. If you have a salary that's 50K, you know that 50K means 50,000. The K stands for 1,000, so we multiply by 1,000. All right, you also know that if you have 20 cents, 20 cents is $0.2, all right, because it's, 100th is 1 cent. All right, so you want to think about it in much the same way. And then milli is 1,000th as well. So you want to make sure that you memorize those ones, and then the others will be, you could use based on a chart or something like that. I don't expect you to memorize. Okay, also, when we talk about standard units in the SI system, the standard unit for length is going to be the meter. All right, so if you think about a meter is about the length of your leg. All right, if you're about as tall as I am, all right, I'm about 5'10". My leg is about a meter long. Okay, so if you're close to my height, then your leg is going to be right around a meter. All right, and if you're a little bit taller, then probably a little bit more than a meter. And if you're shorter, then a little bit less than a meter. But it gives us something to think about. Think about a meter as being roughly the length of a leg. Okay. Um, for time, we're going to use seconds. Everybody's familiar with what a second is, so that's pretty easy. For mass, the SI system, the standard unit is a kilogram. All right, so a kilogram, just to give you an idea, it's about the mass of your Chromebook. So if you pick up your Chromebook and hold it in your hand, that's roughly 1 kilogram. So to give you an idea of what that feels like. Okay, and then the standard unit for electric charge is the coulomb. All right, it's named after Charles Coulomb. We'll talk about coulombs when we get into electricity later on. So no need to really stress over that right now, but that is the standard unit. And then all the other units, every single other thing we measure in science is going to be based off of these 4. Okay, so if we think about speed, for example, all right, speed is in meters per second. Well, that's, length and time. We take those units to do that. Okay, so now on to measurement. In science, what we want to think about is measurements should communicate the level of precision in the measurement. All right, so when you measure something, you are kind of secretly also communicating how precise were you able to measure the particular thing that you wrote down as that measurement. Okay, so for that reason, students should always record measurements to the highest level of precision the device will allow and estimate the last digit. And scientists agree that the last digit is an estimate anytime they look at a measurement. Okay, so this gets us into, and we'll talk more about this in another lesson, this gets us into significant figures and things like that. But the idea is anytime you take a measurement in science, you want to write down all the digits you are absolutely certain of, and you want to estimate the last digit. You want to use the highest level of precision that the device is going to allow you to do, and then estimate the last digit. So I'm going to give you some examples of this in the next couple of slides. So here's our first example. I want you to imagine that this is a metric ruler that measures length in centimeters. All right, so we have this. Now, down at the bottom here, you can see these letters A, B, C, D, and E. So as an exercise, what we could do is we could measure and record some of the measurements that are on this ruler. All right, so I'm going to start with A. All right, so take a look at A in this picture. I can see that A is clearly between 13 and 14 centimeters. I can also see that A, it looks like it's, on the line here, right between 13 and 14. And my estimate is going to be that it's exactly on that line. It doesn't look to me like it's, a little bit between 13.5 and 13.6. It looks like it's exactly at 13.5 to be. But maybe we disagree on that last point. All right, maybe you think there is a hundredth in that place. So for A, I'm going to write down that it's 13.50 centimeters. So I want you to notice here in this measurement that I'm certain it's 13, it's not 12, it's not 14 centimeters. I'm also certain that it's 0.5, it's not 0.4, it's not 0.6. The 0, however, is what we call an estimated digit. It looks to me like there are no hundredths of a centimeter, but we might not completely agree on that. All right, and I think the next example will help to illustrate this point. But the point I'm trying to make here is that notice I wrote down the 0. All right, I didn't just write down 13.5 because I am able to know for certain that it's 13. I am able to know for certain that it's 0.5, and I'm estimating that last digit. We always want to make measurements in this way. Write down every digit you know, and then estimate the last one. Okay, so I'm going to skip now to C. Take a look at C and think about what you might use as the measurement there. All right, so if I was talking about C, I can see that it's definitely between 14 and 15, so I can write down 14 for sure. All right, it's definitely between 0.3 and 0.4, so it's 0.3. But then when I look at this, here's 14.3 and here's 14.4. I'm somewhere in between 14.3 and 14.4. So this is where estimating comes in. To me, it looks like it's a little more than halfway between these two lines. So I'm going to go with 14.36 centimeters. Maybe we don't agree on that 6. That's why this last digit is understood to be an estimate. Maybe you say it's 14.37. Maybe you say it's 14.35. We both agree on 14.3. We might not agree on that last digit, and that's really the point. Write down to the highest level of precision you can, and then estimate the last digit. All right, so then we're going to take a look at one more example, and that example is going to be for this balance. Okay, so let's look at this second example here of measuring mass using a triple beam balance. Now, triple beam balance is something that we don't see a whole lot of anymore. All right, we had some in the lab in the old building, but the new ones are digital. But beside the point, it makes for a good example of how to measure using this idea of significant figures. All right, so this balance is in grams. You can see on the top beam there, it's 0, there's 100 and 200. There's no hundreds. All right, so we got 40, and then we have a 7 here. You can see the 0.5 and the 0.6 there, but the arrow is somewhere between that 0.5 and that 0.6. All right, so I have to estimate that last digit. So when I measure this out, all right, I'm going to say that this mass is definitely 47 point. It's definitely between 0.5 and 0.6, so we agree on the 0.5. But then that last digit is an estimated digit, so it looks pretty close to 0.5. I'm going to say it's 47.53 grams. Now remember that 3 is an estimate. Maybe we don't agree on that. We agree on the 47, we agree on the 5, maybe not on the 3. So no matter what, every single time, measure every digit you're able to measure using the device you have. Okay, so whatever markings are on that thing, you want to measure it as carefully as you can and then estimate the last digit. That's really the point for how we do those measurements.